Okay, so we have been discussing about the rocket dynamics, and in that context last time I told that I will be taking up the specific energy at the burnout. So, specific energy is nothing but the energy per unit mass. At the burnout we can write as 1 by 2 B b square plus G 0 times Y b, where Y b is the burnout altitude, and here Y 0 we are assuming to be 0. Okay. Now, if we divide both sides by G 0 I s p square, okay, so this can be written as B b by G 0 I s p square plus Y b by G 0 S p square. Now, in this format you know that already we have found out the expression for V 0 by G 0 I s p. Here V 0 also we can assume to be 0, okay, and similarly for Y b also we have got the expression for this. So, we just need to insert those expression from the last class. So, this will yield. So, insert the expression here, okay, for V 0 by G 0 I s p and this one. So, once we insert this and solve it, so we get 1 by 2 okay. So, the simplification leads to this equation, and this you can check yourself by putting the expression for V 0 by G 0 I s p and Y b by G 0 I s p square, and plot of the same. If you do the plot here, E b by G 0 I s p and R on this x. So, you will get this kind of curve. So, R is equal to infinity and R is equal to 1, and this is your working range. E v by G 0 I s p, this should be more than the kinetic energy term. Okay, that is this quantity E b by G I, this square here, we are putting a square, we have missed out the square in this place. This is a square, okay, E v by G 0 I s p square. Okay. So, this quantity should be greater than the kinetic energy term which is present here. Why? Because if it is greater, only then you will get the Y b, you will have certain burned out altitude. Okay, now, we will not go into much details of this, we quickly finish the multi-stage rocket. Okay, in the multi-stage rocket, we have one stage here, another stage here, the third stage may be present like this. So, we can assume that there are total of n stages. Okay, and for each of the stage we can have certain specification like the ISP underscore k, this can represent the specific impulse of the kth stage. Similarly, we can write r underscore k as the mass ratio of the kth stage, and along the same line R k can be written as the thrust to weight ratio of the kth stage. Okay, and you know that we have already developed the equations for y v and v v. So, it becomes easy writing the equation here in this place for the multi-stage rocket. Now, let us say we write V k b, the burnout of the kth stage. So, this can be written as V k minus 1 b. So, V k minus 1 b is nothing but V k 0, V k minus 1 b, this is nothing but V k 0, okay, velocity at the start of the kth stage, and this from the our earlier derivation can be written as ln r k as the usual notation we are following. Okay. So, this way we can keep writing for all the stages starting from the beginning. Therefore, the if we add all of them together, so this imply so the terms like for the let us say the previous stage we can write as V k minus 1 b and V k minus 2 b. Okay. So, if you add this kind of terms, so you can see that this term and this term they will cancel out, and ultimately leaving you with the nth stage here, and this is the starting phase, the starting stage. For the first stage, the starting value of V 0 b, okay, which is we will write here V 0 b equal to 0. Okay. So, add them up, and this summation takes place from k is equal to 1 to n. Okay. So, and here also we will put k. So, ln r k minus 1 by r k times 1 minus 1 by r k. So, this gives you the burnout velocity for the last stage. Now, if all the stages are having the same values of a specific impulse and r k etcetera. So, you can just multiply, you can write this as k is equal to 1 to n z 0 I s p times ln r minus 1 by r 1 minus r k, where we are writing r 1 is equal to r 2 is equal to r n, and similarly this summation will then drop out. Okay. This gets multiplied by this quantity r n, and then r 1 equal to r 2 is equal to r n, and similarly I s p 1 equal to I s p 2 is equal to I s p n. So, under these assumptions we can write this statement here. Okay. In the same way, similarly we can write y n b minus y 0 b is equal to z 0 summation k is equal to 1 to n. Okay, where the same symbols as we have used for this the burnout velocity here, the same stands for also the burnout altitude. Okay, so, thus we complete this rocket propulsion part. Now, going back to our the earlier derivation, where we started writing the equation of motion for a rocket in oblique ascent. So, now we are trying to take a more comprehensive view what we have done earlier. Say we fix the x and y axis here. Okay, and a rocket is launched from this place. So, rocket will follow certain trajectory, and this has to be injected in a orbit. So, your orbit may be looking like this. Okay. So, at some intermediate stage, the thrust vector can be written here as we have written earlier, and this is the drag vector. V is in the same direction as the thrust vector. For rocket, the angle of attack is kept 0. Okay. This implies that we will not be showing any lift, we will just write lift equal to 0, and this is meant for avoiding any lateral force. So, rocket is not designed to take the lateral force, okay, unlike the missiles which undergoes very high acceleration along the trajectory and perpendicular to the trajectory. So, rocket is little different from that. So, L is kept here 0, and that is achieved by keeping the angle of attack all the time equal to 0. Now, if we assume that this is the center of the earth, so you can see that the gravity vector, the gravitational force will be directed along this direction. This is m 0, okay. And the local horizontal is defined as the line which is perpendicular to the this m z 0 line. Okay. So, this is the force acting here. Sorry. Okay, and this angle we write it as gamma. This is the flight path angle. Okay, so, you can see that the lift vector, it will be directed some like this, okay, and this will be making an angle of gamma with this line, while if you try to draw this line. So, parallel to this line, it will appear somewhere like this. So, if this is your angle theta, this will be your angle theta. From here to here, this angle we have written as gamma. This is your gamma angle. So, for this kind of motion, sorry. So, if we write the equation of motion for this, so we can write m dv by dt along the trajectory is equal to thrust minus F drag minus m g. You can see from this place here m g is acting along this direction m g 0. So, one perpendicular to this, in this direction you will have m g cos gamma or cos theta, whatever you write. Here we have written this angle as the theta to differ it from this gamma, and this is the usual notation. The gamma is often for even for the aircraft, the flight path angle is described by this symbol only, flight path angle, this is equal to gamma. So, this is the FD, and then in this direction we will have mg sin gamma. So, we can write here mg sin gamma, this is equation 1, and then another equation we can write which is perpendicular to this trajectory. Okay. So, for deriving the equation perpendicular to the trajectory, as you may recall from our earlier lectures, if we have a trajectory like this, and say this is the tangent vector E t here in this place, and this is the tangent vector in this place E t plus delta t or d t. So, this angle, the angle between this and these two vectors, so if it rotates by d phi here, okay. So, if we extend this from here to here, so you can see that the angle between, we are just extending it back this tangent from here to here and meeting it here in this place. So, this angle will be also d phi. So, d phi we are measuring from this direction, and from here the d phi is being measured from this to this direction. Okay. So, in our case, we can take a small part of this trajectory, okay, and which is shown here in this place. Okay. So, this trajectory is shown here. So, a very small length is taken here, which is nothing but here d s. So, d s can be written as, let us say this is rho, okay, which is the radius of curvature of the trajectory, and which will be different from the radius of curvature of the earth. It is two different things. So, radius of curvature we can draw from this place, and let us say that it is lying somewhere here in this place. This is the center of the curvature. You will show it as make it O. So, we will make it C. This is the center of curvature, of the trajectory. This is also called osculating center. Okay. So, this serves as the instantaneous center for this trajectory here in this place. So, d s by rho, this will be equal to d phi. Now, d phi is being taken from this side to this side, and here also from this side to this side. So, this is the positive since we are taking. Contrary to this, gamma is in the opposite direction. So, gamma will be from here to here, and therefore, we will write d gamma equal to minus d phi. Okay, you can see from this place, if the trajectory changes little bit. So, we have the gamma angle here. Say this is the local vertical and this is the local horizontal. So, we measure the we measure the angle gamma from here to here. This is your angle gamma from this place. So, this is the tangent. Okay. So, this is your angle gamma, Okay, you go to a next point which is along the trajectory by ds. So, you will see that the gamma will also change by d gamma, the flight path angle will change by d gamma. So, d gamma can be written in d gamma is equal to minus d phi. Okay. Therefore, writing the equation of motion perpendicular to the trajectory or so this is the this is a perpendicular to the trajectory, okay, and this is a local vertical. They are two different things. Local vertical we decide it from the gravitational point of view, while the perpendicular to the trajectory is decided from the acceleration point of view of the rocket. Okay. So, thus we can write the equation of motion perpendicular to the trajectory as m g cos gamma. This is the m g cos gamma in this direction, and if we write the lift here in this direction. So, this will be minus L, and this we can write as m times the acceleration, normal acceleration, which we are showing here in this direction. Okay, this is the normal acceleration. Okay, so, we remove the this arrow here to which is indicating a vector, because all these quantities are in the same direction, means along the same line. So, and we have already taken care of the sign. So, it can be written in this way, and this is our equation number 2. Okay, so, if we make L equal to 0, putting L equal to 0, now we need to find out what will be this acceleration a n. So, the acceleration along this direction, it is composed of two components. One, due to the, we can assume that this rocket is moving in a trajectory about the center of the earth. Okay. So, in this case we are taking, once we are considering the curvature of the earth is present. Okay. So, one acceleration will come because of this, because it is a moving in a trajectory about the center of the earth. Another one we can see this is locally, that this is also moving about the this center. Okay. So, we can add them and represent the acceleration a n as acceleration due to this is called the acceleration, normal acceleration. So, we will write here the a n equal to normal acceleration, and plus acceleration arising from considering the curvature of the earth. Okay. So, here also we cancel out this m and m. Now, this normal acceleration we can write as, we can recall from our earlier lectures, this is nothing but d s by d t square times E n, okay, where E n is the unit vector in this direction, E n cap. So, we can write this as d s by d t okay. From let us say from our very experience, we know that if any particle is moving in a path, okay, along a trajectory. So, this is the velocity, okay, in the which is tangential to this trajectory. So, the normal acceleration n is given by v square by rho, and here this is directed along this direction. So, v square by rho, and we can put this as n. So, we are cancelling out, this is only v square is appearing here in this place, and we have to have the rho term here present. So, I have cancelled this. So, v square by rho, and where v is nothing but d s by d t. So, this is the acceleration along this direction, and what we call as the normal acceleration. Now, this normal acceleration and another acceleration we are having from the gravitational force. So, gravitational force sorry, due to the movement about the earth, okay, it is also rotating about the earth. So, if it is rotates about the earth, so the acceleration of the rocket, it will be given by, so the acceleration of the rocket due to the curvature of the earth this can be written as, we know that the acceleration is given by m b square, if v is the velocity with respect to the center of the earth. Okay, so, m b square by r. So, r is the distance which is equal to this distance, which is r earth, and plus this distance, which is the altitude h. Okay, so, this can be written as r earth plus h. So, now let us write here d s by d t equal to v, where d s can be written as following this figure. D s can be written as rho times d phi, okay. And if we replace in terms of gamma, so this becomes with a minus sign d gamma, and therefore, d s by d t we can write as minus rho times d gamma by d t, and we write as rho gamma dot. Okay, so, we have converted in terms of the flight path angle, and this is equal to your v. So, what we get here, v is equal to minus rho times gamma dot. So, normal acceleration with proper sign what we have written here, this will be written in terms of gamma. If we write in terms of gamma, then this will be converted into with a minus sign, and this can be written as rho times gamma dot, which is equal to V n times gamma dot. So, this is basically omega. You can see that this is in the form of omega square times r. Okay, so, this is giving you the local acceleration because of this trajectory, curvature of this trajectory, and the same thing we can write as minus v square by rho. Okay, so, this is with proper sign, writing in terms of gamma. Now, adding both of them, so this will give us g cos gamma is equal to a n, and we can write it as v square by rho and plus this term m v square by r e plus h, but this quantity as we can follow from this figure, this quantity is directed toward the center of the earth, as it is moving in a trajectory about the center of the earth. So, this quantity is directed about the center of the earth. Now, we can take a component of this along this direction. So, we will put here cos gamma. So, ultimately acceleration due to the acceleration of the rocket due to the curvature of the earth, here also we can put quantity cos gamma. Okay. So, this completes our derivation. Now, this is our equation number 3. So, equation number 3 combined with equation number 1. This is our equation number 1. So, these two need to be solved simultaneously to get the complete trajectory in oblique ascent, okay, assuming that the earth is having a curvature. It is not here, we are not assuming the earth to be a flat. And see here, obviously, we are writing all the equations in inertial reference frame, not in terms of the non inertial reference frame. As if you try to write in the non inertial reference frame, so what will happen that you need to inject into the orbit. Okay. So, orbit the velocity in the this orbit whatever is, and velocity in the this will be a rotating reference frame, your earth is rotating. Okay. So, if you fix any reference frame here in this place which is rotating along with the earth, then this problem will be there. Then you have to take into the Coriolis acceleration and other things, and if you write the same equation in the inertial reference frame which is not rotating with the earth along with the earth, then the situation becomes different, and you can write the equation in a very simple way. Okay. Thus, we have completed all the equations. And these equations can be integrated. These equations can be integrated numerically using MATLAB. You can do it. Okay. So, here once the rocket is fired vertically, and thereafter it is tilted little bit, and then the rocket follows its own course. So, under the gravitational force itself the trajectory will keep bending, and it is called the gravity turn trajectory. Okay. So, the rocket turns automatically, the trajectory turns automatically under gravity, and this is called gravity turn trajectory. Okay, we have finished all these things. Now, we will take up an example. This is a very simple example, but shows whatever we have done till now. Let mass of a rocket be 60,000 kgs. Okay, so, this is your m. Or say this will put as m 0, and the notations are same as we have done earlier. Mass ratio means m 0 by m b equal to r, this is given to be 10, and specific impulse ISP, this is given to be 400 seconds. And thrust of the rocket, this is given to be 1000 kilonewton. So, objective is to find burnout velocity and burnout altitude and also time to burnout. So, we can take the second problem first. Okay, so, time to burnout, because time to burnout it is involved in the equation for the burnout velocity and burnout altitude. Okay, so, this is the equation for the specific impulse and the quantity ISP is given. Okay, this is given to be 400 and thrust is also given to us. So, thrust is given to be 1000 kilonewton. So, we multiply it by 1000 to get it in terms of Newton, and then m dot minus m dot, and z 0 we can write as 9.81 is equal to 400, and this implies m dot equal to we can solve it, and this will give you minus 254.842 kg second. So, this is the rate at which the mass is being burned. Okay, and obviously, for as we have stated earlier, for all the rockets the m dot is negative. Okay, therefore, dm by dt is given to us, we can integrate it to get the time for burnout. So, dm integrating, or we can write here as dt. Okay, fine. Let us integrate it like this, m 0 to m b t 0. So, t 0 we will assume as 0, and here we will write as t b, and this is equal to dt times t b, and this implies t b will be equal to m 0 minus m b divided by 254.842, this many seconds. So, inserting the values for m 0 we know already. So, m 0 we can take it outside, and we can write here as 1 by m 0 by m b divided by 254.842. Okay, so, m 0 is given to be 60,000 kgs and 1 minus 1 by r is 10. So, m 0 by m b is nothing but r. So, we insert it for 10 and this is 254.842. Or alternatively you could have written as, because m 0 by m b is known to be 10. Okay, so, this simply implies m b will be equal to m 0 by 10 means 60,000 kgs divided by 10 and this is 6,000 kgs. So, here directly you could have subtracted from 60,000 6,000 and this could have been written like the 60,000 minus 6,000 divided by 254.842. So, both are same, this one and these two are equivalent and this will give you 211.896 second. So, this is the burnout time. Now, we can calculate the burnout velocity. So, for finding the burnout velocity, earlier we have developed these equations. Okay, where these parameters you are aware of, this is the thrust to weight ratio and this is mass ratio. So, from here we will have V b equal to, assuming this to be 0, Z 0 times I s p and G 0 is 9.81, I s p is we have taken to be 400 seconds, ln 10 r equal to 10 and this is 1 by r. So, r we have to find it out how much r is. So, r we can write as, we can calculate here in this place, r is thrust to weight ratio m 0 by g 0. So, this is 1000 times 1000 divided by 60,000 times 9.81 and this will give you around 1.699. Okay, so, this is the thrust to weight ratio. So, here we can put it 1699 and 1 minus 1 by 10. So, computing this will give you 6956.709 meter per second or 6.9567 kilometer per second. So, this is the burnout velocity, where we have assumed V 0 to be 0. If V 0 is non-zero, then this will simply add to the V b. Okay, next we take the burnout altitude. Okay, now the for the burnout altitude we have the equation okay, we have written earlier this equation as y b minus y 0 divided by g 0 I s p square to r square Okay, so, using this equation now we can insert the r value and all these quantities are known on the right hand side. This is 1.699 times 1 minus 1 by 10 2 times 1.699 square and if you compute it, this will turn out to be 0.25388. Assuming y 0 p to be 0, g 0 9.81 times 400 square Okay, so, this is the burnout altitude. So, we can see that our once we have put the equation in this parametric form, how conducive it is to calculate the final burnout altitude. Not only that, this burnout altitude helps us in this parametric equation, this helps us in doing the parametric study, that is the most important part. That is the reason why we write the equation in terms of parameters. It becomes because there are various parameters involved and with respect to those parameters how the equation is behaving, that remains the main objective of the study. So, it is not that only once we have done the design and that design then becomes the final aspect we have calculated once. So, if we have a broad aspect of the design like by varying which parameter what happens or in what range it is possible to vary the r, the capital R, the small r, okay, how the system will behave varying these parameters. So, if we have a broad perspective of this, then we do a better design for the rocket. Okay. So, all these details it is not possible to cover in this course, because only 4 lectures are assigned for this. So, but still in the brief we have covered the dynamics of the rocket and we have got a lot of insight into how the rocket motion takes place. And if you remember the earlier what we did, that in the earlier case we assumed the earth to be flat. So, if we assume the earth to be flat and in the vertical ascent obviously this gamma was taken as 0 for vertical ascent. Okay, so, vertical ascent simply implies that we are just going here in this direction, and the sounding rockets generally it is a fired and it goes vertically and it just gives you up to what altitude the rocket is going to get over by the time it burns out, okay, and that becomes a very important parameter. Now, one thing you should take care of here while working out, we have not considered anything about the horizontal motion of the earth. The horizontal motion of the earth, it adds to the motion of the rocket. That is why the rockets are fired easterly. Easterly means as in the last class I have been explaining that if this is earth, okay, and here this is the equator, and if I am firing the rocket in this direction. Okay. So, already the earth is rotating, and last time we wrote the value for this tangential velocity because of the rotational motion of the earth to be around 0.4 kilometers 0.45 kilometers per second at the equator. Okay, so it is a substantial 0.45 means 450 meter per second, while we require for to put in the orbit around 7 to 8 kilometers, okay, 7.5 to 8 kilometers per second. This is the requirement for putting in the orbit. So, even if you are firing the rocket here like this, you are not considering the horizontal velocity. The rocket will keep drifting like this, because it has the horizontal velocity because of the motion of the rotational motion of the earth. Okay. So, irrespective of that, what we have done till now, we have just assumed that rocket is going vertically, and we have written the equation for the vertical motion by putting gamma equal to 90 degree, not 0. This is gamma equal to 90 degree. Okay. This is for the vertical ascent. Okay, remember, gamma equal to 90 degree is for the vertical ascent, and gamma equal to 0 means it is going tangential. And of course, from the beginning you cannot fire the rocket tangentially. So, the rocket is first fired vertically up. Okay, it is fired vertically up, it goes up to certain altitude, while it crosses the dense atmosphere, and thereafter it is tilted, and under the gravitational force, then automatically it keeps bending, what is called the gravity turn trajectory, and all these things can be optimized numerically, and we have to, if we write the exact equation for that, and everything can be worked out in details using computer. But the main objective was here to get the idea about how the rocket dynamics looks like, how do we calculate the burnout altitude, burnout velocity, etc. So, those objectives are achieved by the end of this lecture. Okay, so, okay, for the burnout altitude, we have also written the equation in this format. Okay, this was the original equation without any parametric representation changing much into this. Okay, so, in this V 0, once we are assuming this to be 0, so this gets reduced into this format. Okay. And this equation and the equation that we have written here, both are same, this is nothing different. Okay. And you can check by putting the proper values of T v, we have already known to us 211 point something. Okay. Just now we calculated it, G 0 is 9.81, ISP is given, and this value is 10. So, if you put this and you compute, so I got around 398.517. So, it is a little bit difference from this I am getting, and that is just the numerical error, this kilometer. So, using either the parametric representation or either use the original equation, results are same. So, we end the lecture here, and this whole course comes to an end after total 45 number of lectures. Thank you very much, and whatever you want about the numericals. So, numericals will be putting on the in the web course. So, look for the web course which will be uploaded soon. Thank you very much.